Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kaur and thank you for tuning in. This is Lecture 24, Curve Sketching. Hopefully everyone found the quiz straightforward. I just saw the results coming in and they look good. So it looks like that tutorial helped, and again, hopefully everyone has now brushed up on their algebraic skills and their limits. What today is about is we're going to, oh yes, and excellent. Everyone can hear me. It's always good to make sure there's a sound check. What are we doing today? Okay, yeah, I have one more example to do about the horizontal and vertical asymptotes. And then after that, we go through basically all the things, some of the things that we've done over this course. We'll start to do some curve sketching. So I have a little handy card here, and these are kind of the steps that we'll end up going through. We'll have, number one, we calculate the domain, the X-Intercept and the Y-Intercept, horizontal and vertical asymptotes. We look where the function's increasing and decreasing. We see where there's local min and max. The concavity, if it's, concave up or concave down, inflection points. And the last step is calculating any additional points if necessary to kind of figure out some behavior. So I'll keep that card around, but we're going to, before we get to that, I have one more example that I wanted to do just to make sure that we solidify those concepts of finding the horizontal and vertical asymptotes of a function. So I have an example. And we have this function. We have x over x squared minus x minus 6. And before I have any questions about the quiz, again, if you have questions about that, there's a delay because there's people who are writing accommodated. So again, the marks will get released later. And if you do have questions about the quiz, feel free to come by during office hours because I have lots of time between 1 and 3. Or if you are unable to attend that, send me an email and we can set up an appointment. So again, just a little bit of housekeeping. Okay, so I said, this is to find the horizontal and vertical asymptotes. Now, in the previous lecture, we had actually solved for this. What that is we looked for where that is equal to 0. Again, that's where that function would go off to infinity or negative infinity. So we had actually found in the previous lecture, so previously, it's almost like a recap from an episode. So previously, on our last episode, we showed that x equals 3 and x equals minus 2. Those are our vertical asymptotes. So then to find the horizontal ones, so for the horizontal, we look at the behavior as x goes to infinity. So as x goes to infinity, just a second, I'm just going to check, make sure no drop frames, good. Okay. Okay, so again, like last time, we have this limit is going to infinity. So the way that we handle infinity limits, we pick the largest power. So in this case, the largest power is x squared. So, and what we do is we divide the numerator and the denominator by the largest power. So, in that case, I get x over x squared in the numerator. And in the denominator, I have x squared minus x minus 6 all over x squared. So in this case, I have x dividing by x squared. So that's just 1 over x in the numerator. And in the denominator, I have x squared divided by x squared. So again, I can do this because you can think of that as the x squared being applied to each individual term. So I'm not just saying like, oh, I'm going to cancel out that x squared and boom, I'm done. No, we can't do that. That's an illegal move. So we can't do that. Instead, what I have is I'm going to apply or divide each term by this. So I have the x squared divided by x squared, so that's just 1. In this case, I have x divided by x squared, so that is 1 over x. And lastly, I have 6 over x squared. So what does that mean? If I apply the limit to each of these, well, first of all, we already had a handy-dandy property that we had. We knew that the limit as x goes to infinity of 1 over x to the r, so r is a positive rational, that this equals 0. So that means, so from this, like an easy corollary, a corollary is just kind of a, you have a theorem and then a corollary is kind of like a result that comes from it. That's fairly, what we call fairly obvious. If you set r equals to 1, then 1 over x is equal to 0. And same thing, I have r equals 2, then I have the limit as x goes to infinity of 1 over x squared. That also equals 0. So what that means over here, using my limit rules, I could also kind of rewrite it like this just to showcase what I'm doing. So I have the limit as x goes to infinity. So applying the limit up and down, so that's our quotient rule. Just to make sure that whatever I'm doing is legal. And by legal, I mean like in a mathematical sense, like I'm not doing something that's prohibited. Okay, so I have that. And lastly, so is everyone okay with what I'm doing so far? What I'm going to do now is apply this limit operator to each individual term, and that's by our sum or our difference rule. So I'll have the limit as x goes to infinity of 1 minus, I'm going to put that minus out in front, 1 over x, and I'm also going to pull out that 6 out in front. Over x squared. So this is where I usually kind of pull out a red pen. So the limit as x goes to infinity of 1 over x, well, according to our property, we know that that is going to 0. That pretty much is kind of the end of it. We know that this must equal 0, or hopefully we haven't done anything that's bad, that we've made this denominator undefined. But I have the limit as x goes to infinity of 1. That's a constant, so it's 1. It's going to 1. In this case, I have a limit as that's going to 0. And this part here, I have 6. So this part is going to 0 as well. So 6 times 0 is 0. And I'm just left with a 1 on the bottom there. So just to finish that off, I have 0 over 1, which is equal to 0. And again, it's a similar argument again. So similar for the limit as x goes to infinity of the limit as x goes to minus infinity of x over x squared minus x squared minus x minus 6, and that also equals 0. Again, we had that other property as well, where the limit as x goes to minus infinity of 1 over x to the r is equal to 0, and that was provided that r was a positive rational. Oh, I was going to say here's a rational, so that's, but it also has to be, and r has to be positive. And the other one that I needed to say that x to the r is defined for all x. Okay. So after all that, we had 0 and 0. So therefore, what we can say is that the line y equals 0 is a horizontal asymptote. Okay, so is there any questions about that? Are we all good? Did I go too quickly? What's the next thing that I wanted to say? Okay. It's a little quiet in the chat, so again, hopefully everyone's awake. If not, just say that it's all good in the chat. It keeps me. Again, it's all good. Excellent. Okay. It's 4 o'clock. It's also now tea time, so not like teeing off for golf, but it's like actual drinking. So, what's the other thing that I was going to say? Oh yeah, we have an important property. So there's something important to note. What's kind of important is that a polynomial function has no vertical. Excellent. Okay, good. I like to see that in the chat. Okay, so it has no vertical or horizontal asymptotes. Horizontal asymptotes. Right. So like if we go back to kind of our basic functions that we think of, you know, if we're thinking of a quick polynomial, we have something like a parabola. So there's the parabola. It has no vertical or horizontal asymptotes. There's no number that it's going to. As it's going off to infinity, the limit as x goes to positive infinity of x squared is growing without bounds. So it's we'll write infinity, even though it's not defined. Okay. But we're just saying it's getting really big. And, you know, if we go to the other side as well, it's going to positive infinity. So as x goes to minus infinity, it's going to positive infinity. So again, a polynomial is anything kind of like of the form like x squared, x cubed. The same thing kind of applies for square roots. We know what a square root function looks like. I'll just kind of do a quick sketch. So even for a square root function, so y equals the square root of x. Again, that's growing without bound as well. So again, for both sides, that's, oops, can't do that one. Reason for that is because it doesn't go to negative infinity, because we're defined, again, we're just looking at that function on the domain, and I don't have negative numbers for the square root function. So why, again, like if you wanted to break that down a little bit more, a polynomial has no vertical asymptotes because it is what? In the chat, oh, my internet, I'll have to, oh, okay, Mr. Walker, okay. Is everyone else able to watch this okay? Is there any issues with the connection? Is everyone, yeah, okay. Perfect. Okay, yes. The nice thing about this is that if your connection does go down, YouTube will still keep going. Yeah, okay. So if your internet connection does go down, you're able to watch this later. If YouTube goes down, well, I think we have bigger problems. I mean, because that basically means Google's down, which, oh, the internet could be down. So for everyone. So if, again, that's the nice thing about this. You can replay this later. So going back to this, the domain is all real numbers. That's a good answer. I like that. The domain is all real numbers. Yes. So like over all the reals. But what in particular do we know about the polynomial? It has no vertical asymptotes because it's blank over all the reals. Okay, if you are experiencing some choppiness, I'm just checking. YouTube is saying that it's got a stable connection. So if you are experiencing some choppiness, what you can do is, yes, Mr. Maple has got it. It is continuous. Excellent. Yes, we'll put this in red. This is important. So it's continuous. If, oh yeah, that's another good question, if it's rational. Okay, just going back to if you are having problems, there's a little kind of like gear wheel, and if you click on that, you can drop down the resolution of the stream to whatever, like 480 or 360, if your connection is not high enough for the bandwidth. Yes. Okay. So, yes, Mr. May has got a good question. If it's rational, it's yeah, yep. But with a polynomial, so that's without dividing by something. If a polynomial has, so it's continuous over all the reals, and then that means so there are no infinite, because it's continuous, you can't have discontinuities. So you can't have an infinite discontinuity. Oh, there are maybe I'll just say is. There is no infinite discontinuity. Or there are no infinite discontinuities. If it's rational, that's a good question. I will answer your question with another question instead. So that brings us to our example. I will pick a function. Let's see. Okay, well, let's do that. So this is our example. That's an E. So I have my example. It's going to be y equals f of x. So I have a function and a y kind of going back and forth here. I use a functional notation when I need it, and then I'm using y when I'm graphing. But I have x plus 1 over x minus 1. So again, this is a rational function. This is to answer Mr. May's question. So like, this is my terrible stick man, and he's saying it's a rational function. I guess if I want to be more, maybe it's now a penguin. And there it is. So it's a rational function. So we're going to answer that. We'll bring out this. So we're going to do, so the example would say something along the lines of like sketch this function. So what I'm going to start off with is we're going to start off with the domain. Now, again, we remember that a polynomial is continuous over all the reals. And we also remember that a rational function is continuous on its domain. That's the kicker. So it is continuous on its domain. So that's the first thing that we need to do. To do this domain, this sketching of it. Oh, I don't want to cover the pip. Okay, well, there it is. We'll keep these steps here. So we'll have the domain here. So step 1, what's the domain? Maybe I'll put it, I'm not sure where I'll put this. I'll put it up here for, so we're going to work on the domain. Again, where is it defined? It's going to be defined everywhere except for where that denominator is equal to 0. So we can't have x minus 1 equals 0, which means then that x cannot equal 1. So what's our domain? There's my number line there. So my domain is from minus infinity to 1 union. So I'm kind of skipping over that little hole there. And 1 comma infinity. So that's my domain. number 2. Then we are asked for the X-intercept and the Y-intercept. So you can already kind of see a question forming like this for a test or an exam. You know, you'll have this graph, you'll have this equation, and we'll actually break it down. So like number 1 will ask you what the domain is. Number 2, what is the X-intercept? You know, all the way to the end, and then graph, like from the information that you've concluded from, like draw the graph. So we're going to guide you through it. I don't expect you to memorize, you know, the 8 steps here, even though these are all concepts that we have learned in calculus. So you'd have like some sort of guidance, like part A would be like the domain, part B would be find the intercept, so on, so on. Okay, so the y-intercept is when x equals 0. So I plug in f at 0. So that's 0 plus 1 over 0 minus 1, which gives me minus 1. So my y-intercept is 0, comma, minus 1. And the x-intercept is when y equals 0. So that means I have x plus 1 over x minus 1 equals 0. Bringing the x minus 1 to the right-hand side times 0, that disappears. So I got 0, x plus 1, and then I have that is equal to x equals minus 1. So therefore, the x-intercept is minus 1, comma 0. Okay. Then our third step is to look at the horizontal and vertical asymptotes. So number 3. So step 3, we're working through our steps. So this is the horizontal asymptote. So again, that means that we're looking in the horizontal direction, so we're looking as x goes to infinity or x goes to minus infinity. So the limit as we'll go to positive infinity. So limit as x goes to positive infinity of x plus 1 over x minus 1 is equal to. Now again, I have an infinity here, so I'm going to divide everything by the largest degree or the largest power, and in this case the largest power is 1. So I'm going to divide by x. So it's x plus 1 divided by x. And I gotta be careful, I gotta say my limit as x goes to infinity, and I have x minus 1 over x. So same idea again. Just don't start canceling because I have an addition here. So when I have an addition like that, I can't just go boom, boom, like cancel out the, if you, yeah, like you cannot do this. I'll keep saying it over and over again. You can't do that, okay? That makes me sad. So I will write it out. Just one more step here. Okay. So I have 1 plus 1 over x divided by 1 minus 1 over x. So in this case, I know that this limit here, maybe I will write it out just one more, a little bit explicit. 1 plus the limit 1 over x divided by So we know that this goes to 0. We know that this goes to 0. And the limit as x goes to infinity of 1, it's always going to stay 1. So that's 1. This is 1. So I got 1 over 1. 1 over 1, and that equals 1. And just to save some paper here, similarly, the limit as x goes to minus infinity. So same thing applies. Now instead just put minus infinity here, minus infinity, minus infinity, minus. Still you get minus infinity here. And we knew also that if it's still 1 as x goes to minus infinity, again, that still stays 1 plus, again, this is going to minus infinity, but still 1 over x, that's going to 0. So I'm still left with 1 over 1, which equals 1. Okay, I need some more paper. Okay, so what's the next? I have page 4 here. What's my next step? Oh yes, I have to do the vertical asymptotes. So I haven't finished even my step 3 yet. So for the vertical, my candidate for the vertical asymptote is at x equals 1. So my asymptote should be is x equals 1. However, we need to know what it's going to do, if it's going to go off to minus infinity or positive infinity. So what we need to do is we need to look at our function on the left-hand side of 1. And the right-hand side. So on the left-hand side, so let's think of a small number. So think of x equals 0.99. So if I do that, I have 0.99 plus 1, so that's a positive number. So positive over. Then I have 0.99 minus 1, so that's a really small negative number. Which means that I have a positive divided by negative, so it's going to be a negative. And because this is a small number on the bottom, it means that it's going to be a very large negative number. Large negative number. So just from that analysis, that means that this is going to go to minus infinity. And similarly, we'll do x to the right-hand side of 1. So what we can do is now instead we think of on the right-hand side, so we'll think of x equals 0.01. So again, 1 plus 0.01 is a positive number divided by. Then I have 0.01 minus 1, so that's a very small positive number. So that means that this is going to generate a large positive number, which means that it's going to infinity. So just to kind of recap, if I have this x equals 1, on the left-hand side it's going to minus infinity, and on the right-hand side it's approaching positive infinity. So that's kind of helpful. So This is kind of like our little snippet of the graph, and we'll use that. We'll piece them all together at the end. Okay, number 4, my little up arrow and down arrow denoting increasing and decreasing. So what do we do when we're looking for increasing and decreasing? So in the chat, this is also good review. How do I find the intervals of a function where it's increasing and where it's decreasing? This is good review. So where or how do I find the intervals where the function is increasing and where the function is decreasing? Yes, yes, exactly. Where we look at the first derivative, and we look at where the derivative is positive and where it's negative, right? So that means if it's increasing, that is all the x's where the first derivative is positive, and where it's decreasing is where the first derivative is negative. Excellent. So, see, and this is why we have to do this, is I know it may seem tedious to do a kind of a graph by hand, but it also, it helps to review all the concepts that we've learned so far. It gives us a little time to kind of review everything that we've learned. So that's our function that we have. I'm going to take the derivative of this. So I'm going to use the quotient rule. And again, the quotient rule is the derivative of the top function times the bottom minus the top times the bottom function, the derivative of the bottom function, all over the bottom function squared. So I'm going to take the derivative of the top function. So the derivative of x plus 1 is just 1 times the bottom function, so that's x minus 1 minus the top function, so that's just x plus 1 times the bottom function, the derivative of the bottom function. So the derivative of x minus 1 is just 1 all over the bottom function squared. Okay, and that's our quotient rule for derivatives. Let's fix this up a little bit. Again, it's always going back to the question of, do I have to simplify? This one we can clean up a little bit nicer. So minus 1 all over x minus 1 squared. So this case, I have the x's cancel, and I have minus 1 and minus 1, so that gives me minus 2 over x minus 1 squared. Okay. So again, to find where we break up those points of where the function is going to be, switching from increasing to decreasing, we look for the critical points. Now, when I had introduced this, critical points, I had probably said that the critical point is where f prime at x is equal to 0. Okay, so if we start to do that, we run into a problem. The problem is I set this equal to 0, and what happens is I can then bring that over to the right-hand side so that I get minus 2, and then I have 0 times x minus 1 squared, but that means that 0 equals minus 2. So that is not possible. So you're going to be asking me, oh no, what are we going to do? Like, we need to be able to find something where it's going to be changing or something like that. Like, how do we break up our intervals, like our real line? Okay, don't panic. The other point where it's interesting, and I'm going to use the word interesting, of a derivative is where it's equal to 0 and where f prime at x does not exist. And you're like, holy smokes, what do you mean it doesn't exist? Well, what we can do is look at this function here, and we know that we need to look at its domain. We look at the domain of that derivative. And so we need to look at the domain of f prime. And in this case, again, we have something in the bottom here. So I have x minus 1 squared. So that denominator cannot equal 0. So that means that x minus 1 squared cannot equal 0, which then means if I square both sides, squaring the 0, I get 0, and I get minus 1, x minus 1 on the left-hand side, and x cannot equal 1. So that means that f prime is discontinuous at x equals 1. Or another way of saying it is that f prime does not exist at x equals 1. So that is our critical point. This is also a critical point. So let's so a critical point is x equals 1, and that's where f prime does not exist. So we want to see what it's like around that discontinuity then. So around x equals 1, we'll then be able to break it up. We'll look at the two intervals from minus infinity to 1, and from 1 to positive infinity. Is everyone okay with that so far? I haven't scared anyone yet by because we've talked about functions of being discontinuous, but yes, also the derivative can be discontinuous as well. Okay, perfect. So I've broken that up. Now we just will test some points. So we'll look at, say on this side, we'll pick a test point. I should write out my f prime at x is equal to minus 2 over x minus 1 squared. So if I pick a point in that interval, so pick it easy, so we'll pick it 0. So I get minus 2 over 0 minus 1 squared. That means that I have minus 2 over 1, which means that it's minus 2. That's less than 0. So that means that derivative is less than 0. So on this interval, it is decreasing. And if I look to the right of 1, I'm going to pick 2 as my test number. Also, Mr. May, make sure that you're watching my negatives, right? It's always good to have crowdsourcing the answers. More tea, like there's a cup of tea there. Right, 2 minus 1 squared minus 2 over 1 squared. So that means that's minus 2. Again, that's less than 0, which then means that the derivative is less than 0, which means that it is still decreasing. So it's decreasing on the left of x equals 1, and it's decreasing on the right of x equals 1. Okay, let's go back to our steps. Our program says, okay, then it asks, oh, where's the local min and where's the local max? So is x equals 1, just looking from this, is x equals 1 a local min, a local max? Just what do you guys think? Everyone, I mean everyone. Is x equals 1 a local min or a local max? A min, okay. This is good time to review. It's neither. Yes. Yes. This is a good time to review again. If I have x equals 1 here, if I had it decreasing and I had it increasing, you know, I kind of have this valley here, then that's a minimum. If I have it increasing and I have it decreasing to the right of 1, then this is what we call a max. If I have it decreasing and decreasing, it's just decreasing, and then again we could have it increasing and increasing, you know, it's still just increasing. So it's when it switches from an increasing, so from an increasing to a decreasing, that's a maximum, and from a decreasing to an increasing, that's a minimum. Someone wrote max. What? Did I do something wrong? Here's the min. Here's the max. So, in this case, there is none. So there's no local min and no local max. The function f, the original function, point of inflection. Well, we'll get to that, number 7. But remember that a point of inflection is the point in which it's switching concavity. And so we're not talking about concavity yet. This is the first derivative. So the first derivative is talking about increasing and decreasing. And when we get to the second derivative, that's when we start to talk about concavity. So it might be a point of interest. We'll have to find out. I'm just going to finish off saying that the function f is decreasing on the interval from minus infinity to 1 and union 1 comma infinity. So yes, this is where we get to the concavity now. So we'll work through our steps now. Yes, we need a second derivative for that. Exactly. So number 6, we're doing concavity. So we need the second derivative. So just as a review, if the second derivative is positive, then that means that it's concave up. And if it's negative, if the second derivative is negative, then it's concave down. So, okay. I don't know why my voice went up that high. Yeah. Okay, so we need to find the second derivative. And, well, we've done the work for finding the first derivative. So again, this is not, sometimes it's easier to just rewrite it, because what I'm going to do is I'm going to rewrite this function to give me minus 2 times x minus 1 to the minus 2. So again, if you see stuff that's in the denominator and you want to rewrite it so that it has a negative exponent, that's okay, because what I'm going to end up doing is I'm going to use chain rule for this. So I have f double prime. So I have f double prime, and I'm going to take the derivative. So I got minus 2 in the front. That minus 2 comes down in front. I leave the inside alone. And then this reduces down by 1. So I got from minus 2 to minus 3. I know it's a bit weird because we're used to dropping it down from like 2 to 1. But when we have a negative, minus 2 minus 1 gives me minus 3. And I'm not done yet. I still need to take the derivative of the inside. So the derivative of this inside function here. So I'll explicitly write this out. Because I have to kind of rewrite this a little bit nicer. So I have 2 times negative 2. Sorry, negative 2 times negative 2 gives me positive 4. I'll rewrite this. Minus 3. And then the derivative of this. So the derivative of x is just 1. And then I have a constant that's 0. So it's just times 1. Okay, so again, we were looking for the critical point again. If we set it to equal to 0, I have the same issues again. If I set that equal to 0, then if I bring that over to, I have 4 equals 0 times x minus 1 to the 3, then that means that this goes to 0 and I'm left with 0 equals 4. That's not possible. So again, we're going to look for the points where it's equal to 0 or it's not defined. So in this case, it can't equal 0 because then it's undefined. And notice that where the original function was undefined, that our derivative was, the first derivative was undefined. So in this case here, it's very interesting because the derivative is inheriting kind of the domain. So again, that was, we have the original function is not defined at x equals 1. We find that the first derivative is not defined at x equals 1. And similarly, again, the second function, or the second derivative, is not going to be defined at 1. So again, I'm going to cube both sides. So cubing, or taking the cube root. So taking the cube root of 0 is still 0. X minus 1. So that's one of our points to look at. So I'll do the same thing again. I'll just kind of break it up, our interval. So we have x equals 1. And I have minus infinity to 1. On this side, I have 1 to infinity. And I had my derivative, my second derivative, was equal to 4 over x minus 1 cubed so pick a point inside there. I'm going to pick 0, so I'm picking a point in that interval. 4 over, and all I'm looking for is the sign, so 0 minus 1 cubed. So in this case, it's cubed. Minus 1 cubed is still minus 1. And so I have minus 4, which is a negative, which implies that it is concave down, meaning something like that. On the right-hand side, I'll pick something like 2. So I have 4 over 2 minus 1. So 2 minus 1, that's 1 cubed, which means it's still positive. So that means that my f at double prime at x greater than 0. So it's concave up. Okay, so you might start thinking, okay, we see that x equals 1 is switching, you know, on the left side of it, it's concave down. On the right-hand side of it, it's concave up. So for our point of inflection, you'd be tempted to say that there's a point of inflection at x equals 1. So let me just put that down. So this is points of inflection of so you might be tempted okay, I'm gonna put that I mean, like, this isn't like chocolate cake. You might be tempted to say x equals 1 is a point of inflection. But why is it not a point of inflection? What do you guys think? What do you think? Why? Can you give me one a reason for why it's not a point of inflection. Exactly, it's discontinuous. Yes. But f at 1 is not defined. So it can't be a point of inflection. So therefore, there are no points of inflection. Yes, because we have our vertical asymptote at x equals 1. Yep, it's discontinuous, it's not defined, we have a vertical asymptote. Yep, all of that. Which means that it's the graph is doing some concave down on, by the asymptote. So on that side, and that also, coincides with our other information that we had looked at, that at x equals 1, it's going down, and on the right-hand side, it's going up. So we can have a concave up function on this side, and we can have a concave down function on the left-hand side. So this is all good. It's confirming what we've kind of discovered in our previous steps. So number 8 says additional points if necessary. If necessary. So if you don't know, something doesn't look right, or oh, sorry, I didn't mean to hit the microphone. This is the point where I start to use a ruler. So again, like on a test, feel free to get a ruler. Let's see, got something like that. And here's my x-axis, here's my y-axis. And I pull out my sheets again. So I get, what's all this stuff that we know? So the first one is that we know that, we know that the domain, so there's something happening around x equals 1. We have 0. Okay, I should mark off some points here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So I'll say this is 1, this is 1 here. Okay. So I said my y-intercept is at 0, minus 1. So 0, 0, minus 1. The other one that I know is that minus 1 is equal to 0. Okay. Oh, I have my horizontal asymptote, which we know that horizontal asymptote at y equals 1. So we'll draw in that. Maybe I'll use this. There we go. Okay, so we're going to do that one. What's the next thing? We know that there's a vertical asymptote at x equals 1. So I have y equals 1. This is x equals 1. Beautiful. Okay, so that means, and I can kind of see this already, that it's going to be going down and this is going to go up. So just as a little reminder, something like that. And then it's going to go up. Not sure what I'm going to do here yet. So something like this, up, up. So let's deal with that. Okay. Where is it? Increasing. So this is the increasing part. We saw that it's decreasing and decreasing. So like this part is fine. So we can kind of see that something like that, it's going to be decreasing. And this has to be decreasing as well. So I don't know, something like that. Okay. There's no min and no max. That's looking right because it's going to be going off to infinity and this is going to go off to infinity. So it's never going to actually get to that minimum. And we have our concavity. So what did we say? That is concave down for up to 1. So it's concave down. And concave up. So something up like that. So something like that. And that's where we start to sketch. So I kind of I have something like this. So here's my asymptote. I know that it needs to get really close to that. And I also know that it has to get really close to this as well. So it's going off to infinity here. That was because we found that. What the behavior like was to the left of x equals 1. And from the right of x equals 1, we know that it's coming from positive infinity. And then it has to say concave up. So it doesn't cross this because if it does, it's got to keep decreasing. So if it goes below here, if it does something like this, if it crosses that point, then at some point I actually have to come back up and I have to come back up, and to have this still be a horizontal asymptote, then it has to actually switch concavity and draw that. And that's not possible because for this entire interval from 1 to infinity, we know it's concave up. So it can't switch from concave up to concave down. So it means that it has to stay the same concavity. So that one is not possible. So it means then to keep the concavity and to keep it decreasing, something like that. And that's our function. It's a quick sketch, right? Like that. And by quick, I mean, we didn't have to do a table of values. We did this all using concepts from calculus. So again, as a recap, we knew that the domain was not defined at x equals 1. We knew that we found the X-intercepts. So we found the X-intercept and the Y-intercept. We found the horizontal and the vertical asymptotes. We found where it was increasing and decreasing. And we actually found that it was decreasing from minus infinity to 1. And it was decreasing from 1 to infinity. We found that there was no local min or local max. So again, if you look at this point here, there is no local min or local max. Like that function keeps going on forever. It's going to get really close to 1, but it doesn't actually get to that value. Remember, it's that limit. It's getting really close, but it doesn't touch it. And same thing with this one. It'll get, if you thought it was going to be a min, it doesn't get to it. Again, because it's as the limit goes to infinity, it gets really close to 1, but it never actually attains that number. Then we found the concavity. So the concavity was concave down between minus infinity and 1, and concave up between 1 and infinity. And because of our second derivative, we weren't able to solve it for equaling 0, but we were able to find where that function was not defined, and that again was where it was not defined at x equals 1. So we looked at that, but that means that we had no points of inflection. Again, because it had changed concavity, concave down and concave up, and we would have expected a point of inflection. We could have had a point of inflection, except for the fact that the function is not continuous at that point. So we don't have a curve to switch it. So again, that's why we don't have a point of inflection at that. And that's it. That's our graph. Oh, there's my page 3. I keep these all in order. Okay. Let's do a second example. And because of, hopefully I've explained everything, that we might be able to go a little bit, well, with ease through this. So I have my function f at x is equal to x cubed minus 6x squared plus 9x plus 2. Number 1. We're asking what is the domain? And the domain in this case, what is the domain in the chat? I have a polynomial. Ooh, somebody wrote E. Okay, yes, it's all the real numbers. Excellent. Minus infinity to infinity. Yes, perfect. Good. And next we have the X-Intercept. Let's do the Y-Intercept. So at this point, that's when x equals 0. So I substitute in my value f at 0. So that gives me 0 cubed minus 6 0 squared plus 9 times 0 plus 2. That's 0, 0, 0, and this is equal to 2. This is when y equals 0. So that's saying that I need to solve that 0 equals x cubed minus 6x squared plus 9x plus 2. Okay, so that's solving a cubic equation. Solving a cubic equation is beyond course expectations. Okay, meaning that, oh, you know, it's difficult. And we don't expect you to solve cubic equations. And I will confess that if I had a cubic equation, I pull out my recipe book. Here's my recipe book. It's the CRC Standard Mathematical Table and Formula. And I would flip to my pages that I have marked. Oh, I marked it already here for you. So again, this would tell you, this is like a cookbook, and it would tell you, okay, I have a quadratic equation, here it is, here's the formula for it. And again, right in here, that's our discriminant and tells you how to solve that. But to get to a cubic polynomial requires a little bit more cooking. In this recipe, you'd have to find the roots, and you have to perform the following computations. So here it is, step 1, step 2, step 3. When you get to step 4, you have a condition where like it could be 3 real roots. You continue forward, doing another 4 calculations, and then again checking to see if you had a 1. So that's the case where you had 3 real roots, and then you can have 1 real root and 2 complex roots, so on and so forth. So you can do it, but it's beyond the course expectations. Of course, you would ask, can you do a quartic? Yes. This is the the method for doing the quartic. And it keeps going up onto the others page. So this is just a little caveat. All polynomials of degree 2, 3, or 4 are easily solved by radicals. That means that you can find their roots using algebraic operations and taking the root. And if you need to solve higher degrees, then they can't be solved by radicals. And that's getting more complex. But, so there is a formula to solve the cubic equation, but again, it's beyond course expectations. But I am not going to shy away from telling you that it is possible. There is a cookbook for it. And if you were really inclined, you could do it. But, so we'll say that's beyond course expectations. Number 3. This is the horizontal asymptotes. Oh, and you don't have to go buy that cookbook. I keep it in case I... Basically, when I have a headache or I forget something and I need to look up something really quickly. It's kind of like an encyclopedia of math. And so in this case, I'm looking at the limit as x goes to minus infinity of this function, but we should be remembering that it's a polynomial. So it has no vertical or horizontal asymptotes. So why am I even bothering looking at this? It's going to go off to minus infinity. And then this one here, positive infinity. So I'm gonna say remember polynomials don't have asymptotes. Okay, so they don't have asymptotes, so I don't have to worry about that. Or vertical. So none. Therefore none. Okay, so number 4, I look for where it's increasing and decreasing. So number 4, increasing and decreasing, which means that I need to find the derivative of that. So I'll just copy that down again. So I need to take the derivative of this function. So just using the power rule, straightforward. And after that, I need to find the critical values. And again, I got a polynomial, so it means that it's continuous, which means that this is defined for all those x's. So I don't have to worry about any points of this function where it's not defined. So it's a polynomial, continuous, which means that it's going to be defined everywhere. Don't have to be concerned where it doesn't exist. Okay. There's my chain of thought there. So with the polynomial, it's continuous, it's defined everywhere. Don't have to worry about where it doesn't exist. So we can find our critical values. So critical values is where that derivative is equal to 0. So factoring that out, I get 3 times, okay, so I'm going to pull out 3, so a common factor of 3, and I'm left with x squared minus 4x plus 3. And then I can do another little factor here. I have to make sure that it multiplies to give me 3 and adds to give me minus 4, so it's minus 1 and minus 3. So minus 3 and minus 1 gives me positive 3, and minus 1 and minus 3 gives me minus 4, so that's good. Which means then that my critical values to look at is at x equals 1 and x equals 3. Do 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 do. Okay. So I'm going to break up my number line. I have x equals 1 and x equals 3. So that means from minus infinity to 1, 1 to 3, and I have 3 to infinity. So my derivative if I pick f prime at 0, so that's 3. Okay, I have a minus 1, so that's a minus, so I have a negative, and a negative gives me a positive, and times 3, that's still positive, so that means that it should be positive, and maybe I'll just write that out. So 3 times, so I got 3 times minus 1 times minus, which gives me minus 9. So that means that we are, oops, yes, I forgot. There we go. So it's negative, which means that it is decreasing. If I look in the middle here at, say, f equals 2, I'll have 3 times 2 minus 1 gives me 1. 2 minus 3 gives me negative 1. So that gives me minus 3, which is less than 0. Oh, did I? No. Sorry. Joe, where are you? Like, I have a positive and a positive. That makes it plus 1, or plus 9. Yep. Good. This is the magic of this tape. This is awesome tape. Okay. So that's greater than 0, so that means that, there we go. Right here, this is less than 0. Good. Good. I want people to be catching my negatives. Am I 4? So again, I have 3 times 4 minus 1 is 1. 4 minus 3 is 1. So that's equal to 3, which is... Did I do that right? So 3 times 4 minus 1 is 3. 4 minus is 1. So this should be 9, which is greater than 0. Excellent. Thank you. So everyone got 9. Excellent. Okay, so this means that I expect, so here's kind of my, I'm going up a hill and coming down, so this means that I have a max. I'm going down and then going back up, so this means that I have a min. And so that brings us to the 5th point, is our local min and max. And we know that the point, we know it's a max at x equals 1. But we need to plug that point back into our original function right down here. So f at 1 is equal to 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. So 1 minus 6 plus 9 plus 2, 6. Make sure you check my arithmetic. I'm having an off. Well, it's been an off week. So our max is 1 comma 6. That's our point. Is that correct? Make sure. 6? Good. Yep. Excellent. Good, good, good. We're going to say there's a min at x equals 3. So again, I plug that back into my original, because again, I'm looking for the points on the original function at this point, right? Because I'm going to be plotting those points. So again, my function at 3 gives me 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2. Okay, so move that page out of the way. 3 cubed is 27. 3 squared is 9. 9 times 6 is 54. 9 plus 3 is 27 plus 2. So I can actually 27 it gives is, so this is actually right here, that's minus 27. Half of 54 is 27, so minus 27 plus 27 plus 2, so minus 27 and set 27, that cancels, so I'm left with 2. Oh, we got minus 25. Okay, I'll pause. Somebody double check. I mean, 2? I got, okay, got 2. Okay, okay, 2, good. Yeah, 9 times 6. 9 times 6. 6 comes back, so I have 54. So, yeah. And so I have a 3, 2. So we're at step 5, step 6. So my step 6 here, concavity. Okay. So I have my function here. So I'll just copy this down. So I need, for the concavity, I need my second derivative. So I know what my first derivative is. It's 3x squared minus 12x plus 9. And then I'm going to take the derivative of that. So my second derivative, 3 times 2 is 6x, and that drops down by 1, so I'm just left with x minus 12x, so the derivative of 12x is just 12. I'm going to just factor out that 6. There's a common factor of 6, so I'm left with 6 times x minus 2. Which means that if I set this equal to 0, this could be an inflection point. And it's good, it's part of our domain. So okay, let's finish this. Let's see if I can try to finish this up. So my point here, I have x equals 2. So I'm going to look to the left-hand side. I'm going to pick 0. So I got 6 times 0 minus 2, which gives me 6 times minus 2 minus 12, which is less than 0, which means that my second derivative is negative, and that means that it's concave down. On the right-hand side, if I pick a number, say 3, then it's 6 times 3 minus 2, 6 times 1, 6, which is greater than 0, which then means that it is, the derivative is positive, and that means that it's concave up. And then probably it's very similar to what I taught last year. Exactly. Oh, yeah. I didn't use my fingers. I should. Okay, yeah. So, points, my 7th, last one here. So my point of inflection. I do have a point of inflection at x equals 2 because it's switching concavity from concave down and concave up, and x equals 2 is in the domain. So x equals 2 is point of inflection, which means I also need to plug that point back into the original function. So I have 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2. So that's 8 minus 24 plus 18 plus 2, which equals 4. So my point of inflection is at 2, 4. Oh, I'm running out of time. All right. We're almost done. What am I doing? What am I doing? What am I doing? Okay. So I know. What do I know? What do I know? What do I know? 1, 2, 1, 2. So I have my points of my Y-intercept. I know that it's at, my Y-intercept is at 0, 2. So plug that. I know that, what else do I know? I know I have a max at 1, 6. So 3, 4, 5, 6. Here's a max. I'll kind of write something like that. I have 3. Here's 2. Something like that. There's my min. Here's my max. Ooh, this is going to be a fast sketch. I know that I have a point of inflection at 2, 4. So 2, 3, 4. At 2. Right about here. Point of inflection. I also know that it's concave down as it comes up to 2, so it's concave up. So something like concave up, and then it switches concavity and goes concave down and concave up. So concave up around here, concave down, and go through this point. There we go. And that looks like a cubic function. That's what we expected. And it's, again, we have a positive, so we kind of expected it to have some sort of shape with point of inflection. That's x cubed. So there is our function. It's a quick sketch without doing, except for maybe one point, to do the table of values. Like, we didn't have to do that. So thank you all for sticking in. If you have any questions, feel free to send me an email. You know my email address through the RMC server. Thanks everyone for participating and keeping it active. It's very important. And I hope that this is a good summary and a good review also for our upcoming test that's coming up. Not this Thursday. I don't want to panic everyone. It's come on. It is the 25th is when I plan to have the next test. So thank you all for tuning in, and I'll see you on Thursday.